Welcome back. So let's proceed now to the next lecture, which is index construction. So we've set the basis of everything in the first weeks, right, for Boolean retrieval, and in particular, I can never show it enough. That's the standard inverted index that now you know by heart. We have the terms organized as a hash table of B+3. We have the document frequencies in purple. Here I forgot to put the font in white, but you can still count, so it's redundant. And then we have the postings list, which are sorted lists of integers. And we'll see why sorted is so important next week when we cover index compression. All right. So we have the hash tables and the B+3, so it's especially the B+3s to index the words. In fact, it's not only the terms, but also the permuterm index, the soundex, the k-gram indices, so many that use the B+3. We are able to execute wildcard queries. We know how to do it if the wildcard is at the end, if it's at the beginning, if it's in the middle. We even have several ways of computing wildcard queries with the permuterm index, with the k-grams, for example. And now we can do spell correction with the k-grams, with the edit distance, and with soundex, and with the Jacquard coefficient, right? So you have 4 different building blocks for the spelling correction. So the permuter index, that's where you rotate things. So you write the word on a ring and plus $1, and then you rotate, find all the rotations. The k-gram is different. You still put $1, but this at the beginning ends the end. Then you have this sliding window over your terms. That's the k-grams. Notes that the k-grams have a parameter. K can be 2, can be 3, can be 4. The permuterm doesn't have a parameter. It's just always the same. Then we have the edit distance that tells you how many steps you need at least to go from one word to another word. We have the Jacquard coefficient, that is the ratio of the intersection cardinality divided by, so I already said with the ratio of the intersection cardinality and the union cardinality. Soundex, that gives you this phonetic fingerprint that you can also build an index on with the B+3. So this is what we have seen so far. Now we are going to take it to the next level because you did it in an exercise on something that fits on a laptop, right? Who did the exercise with the Boolean querying? Who had fun? Okay, very good. So now, what if the collection that we want to index is much larger? Then as you can imagine, the way that it's implemented in the Jupyter notebook is not going to be very efficient, right? At some point, you will see it start slowing down or, you know, not as fast as it could be. So now the point of this lecture is to try to squeeze every inch of performance and space that we can from our laptop. First the laptop, then we'll go to clusters of machines in a data center. That's the coolest part. But you wouldn't believe what you can do already on a single laptop in terms of squeezing performance out of that. But for this, we need to look at something that I find very scary. It's hardware. I don't know much about hardware, but what I do know is on the high level, roughly what it does, right? So the CPU is kind of computing things, right? It has its registers, and with the von Neumann architecture, it's just computing bits out of bits, right? So that's the CPU, it's the brain of the computer. Then you have the memory where you maintain all the structures, the data structures and so on that you are building. So ideally, maybe this is where we want to have the standard inverted index so that we can query it, but you still have the disk, right? So in the long term, you might want to also save it here, but it's going to be slower. So you still can find the memory useful, right? So we have also the hard drive or the SSD. Right, so the main difference at my level is that if you switch off the electricity, this goes away, this doesn't, right? And then we have the network switches that allow you to communicate in a data center, right? That you need to consider. Now, you probably think that's very trivial what I'm telling you, and I think you might even know more than I do in terms of hardware. But the reason that I look at hardware in that way, or at least database people look at hardware in that way, is that when you have a performance issue with databases, you can always say with certainty it's one of these 4, the bottleneck, what's making things slow. It's either going to the CPU or the memory or the disk or the network, one of the 4. And so when you try to fix bottlenecks, you have to find out which one of the four it is, and then you improve your system in order to do that. So again, it sounds trivial, but there are many people who don't look for the bottleneck, and they just go ahead and start fixing things, and then it doesn't make a difference. Well, it doesn't make a difference if you're not working on the right one, right? You really need to find the one that is the actual bottleneck of your system. So we'll need to look at it on the high level a little bit now in order to make sense of this, to have a better algorithm for constructing the standard inverted index. So again, this is a recap of what we have in terms of memory hierarchy, right? So we have the memory and the disk, but we also have the cache that is even faster, but of course, less quantity, less storage. And then we have at the bottom, the tapes, DVDs, if that even still exists, but the tapes, they still do exist at ETH. They still have tapes somewhere. It takes a lot of time to retrieve, but this is where the backups are. And even though it's slow, it's important for durability, right? But what's important is that you need at least the disk for long-term storage of your collection and index, but you also need the memory in order to execute the query, right? So it's roughly going to be between the memory and the disk, the purpose of the discussion today, right? Okay, so slower to read, it goes like this. It's slower to read on a tape than the cache of a CPU. Of course, it's more expensive per byte on the cache than on a tape, right? Okay, but I'm probably boring you. I mean, you're computer science students, and I'm sure you know all of that. All right. But what I want to make you aware of is these factors: capacity, throughput, latency. I repeat that almost in every one of my courses. If you look at capacity, it's how much data we store. Like, for example, that would be the number of words in a book, in that case, 600,000. Then you can look at the throughput, which is the speed of transmission of the data, right? So it could be 1,000 words per minute if you read the book. And then there is the latency, which is when you start receiving data, which takes time. With tapes, it's going to be several hours. With a hard drive, maybe, I don't know, a few milliseconds. And at the memory level, maybe microseconds, maybe even better than that. Right. All right. But anyway, and the latency in the case of the books is 1 minute to stand up, go to the shelf, pick the book, and so on. So that's just the real world illustration. But the thing is, if you look at the evolution of what has happened in the past 70 years, it's an absolute catastrophe. It's an absolute catastrophe because the capacity has enormously increased. What you can store per unit of volume has increased. And the throughput, in comparison to capacity, has increased by that much. This is how faster you read your data, but this is how more data we store. And now we see we have a big problem. And the capacity, you barely see it because it should diminish. It's better when it's less, but it has barely changed. So this is a huge catastrophe, and this is why we need to come up with all these new ways of dealing with data to compensate for this big issue, right? All right, so these are the sizes in there that in memory you fit 8 gigabytes, 4 terabytes. It's more than before, right? It used to be, it's more than even what you have on disk before. The disks, they can store, let's go to 12. I think now we go to 26, maybe even 30 terabytes by the end of the year. And the tapes can go to the petabyte range, just so you know. But the collections we want to index, they might or might not fit in the memory and on the machines, right? And that is a challenge that we need to address. But even if they do fit, it might still be too slow to actually read them. So I just did a recap here of the common sizes to expect. Here, that would be the latency. It's even 100 nanoseconds for the RAM, milliseconds for the hard drive, and these are the throughputs. It's just orders of magnitudes of what you can expect. For the disk, you have to consider again the SSDs versus the hard disks. But the hard disks, they are still popular because first they are cheap, and then you have more capacity. So this is why we still have a lot of them in data centers when we want to store a lot of data, right? So you need to understand that in a mechanical drive, so those that are cheap, you have these rotating parts, and this is why it actually needs time. This is the reading head right here that is reading the data, and this is rotating. And when you have the head somewhere, you have to wait until this rotates all the way to the head, right? So this is where the latency comes from. And so if you read randomly from the disk a little bit everywhere, then this is going to take forever, right? So this is what's important to understand. So this is why we read in blocks from the disk. Because imagine that you just fetch one single byte. You want to fetch 8 bits, 1 byte from the disk. Where's the time going? Well, you're probably going to spend almost all your time waiting for the disk to rotate, to be below the reading head, and then immediately you read the byte. So you spend most of your time actually lost in latency, wasted basically. Latency is almost wasted time, right? So this is the reason why we never do that. In fact, we never read single bytes from the disk. Instead, we read in blocks. So the order of magnitude, it can vary, right? But it can be, 4 kilobytes is a typical number. So here, 64, I think I probably meant 64 kilobits, probably. That would be 8 kilobytes. This is the order of magnitude, right? A few thousand bits or bytes at the same time, all right? So we do that because if instead of fetching a single byte, we fetch one block, then we spend a bit of latency, right? Of course, we still need to wait for the head to be above the rotating disk. However, now we will spend a lot of time transferring bytes, right? So the time is spent in the actual byte transfer. This is where the added value is. So now if you have a lot of data to transfer, this is much better if we repeat that 1,000 times. After 1 hour, we'll have transmitted much more data this way than this way, because here we would just be constantly waiting. For whom is that clear? I'm assuming that many of you have seen this before, but I want to make sure that from an abstract perspective at the high level, everybody is clear with that, right? So we read in blocks from the disk because we want the throughput to be high and we don't want to waste our time waiting for the rotating parts to be at the right places. Okay. So the conclusion of that is that the data is sent to and from the memory in blocks, right, of roughly 64, I probably meant kilobytes here. It's only the order of magnitudes that matters, right? It doesn't really matter if it's 4, 8, 64. It's really just thousands you should have in mind. All right, so data is sent to and from memory in blocks. That's the first thing to know. Second, you also cache some blocks in the memory. So if you read repeatedly the same thing, then you actually can still remember it in memory and not read it again. So this is basically called caching, that I'm assuming also everybody knows. And now, speaking of bottleneck, I told you the bottleneck is either the CPU or the disk or the memory or the network. In the case of systems that are data intensive, the bottleneck is typically going to be the disk. The time is typically spent on actually reading from the disk. So what that means that the bottleneck is the disk is that the CPU is going to be idle most of the time. You're not using the CPU to full capacity. What's slowing things down is just reading from the disk. So when you have this imbalance between the disk that's completely overloaded and the CPU that is completely idle, then you can compensate by doing something called compression, because what happens if you compress the data? You're going to have less to read from the disk, right? And the CPU will have more to do. But it's fine because the CPU was idle anyway, right? So you're basically rebalancing a little bit the workload from the disk onto the CPU by doing compression, right? So a way of looking at compression is this. You can also look at it from an information theory perspective in terms of entropy and so on, but for this, compression actually means transferring a bit of the bottleneck from the disk to the CPU. This is what's actually going on. All right, so I just wanted to set up the abstraction here of hardware in here, and there is no need to understand further details of the hardware than just this very high level, naive way of looking at it. So, still have a few minutes. So I'll start with a first optimization that is commonly done when we build indices, and this is called term IDs. You already heard of document IDs, right? But term IDs, I hadn't mentioned them until now. So in a standard inverted index like this, you have the terms on the left and the document IDs, but the terms, it's not term IDs, it's terms, right? So now, if you look at it from a logical perspective, I'm going to show you something that I have told you many, many times, including at the beginning of the lecture today, is that this here, for example, 3 is a posting. It's not just document 3, it's the pair of document 3 and data. It's technically data 3, right? So now if we explicitize these things here, and we add back this term to every document ID, then these are the postings. These are pairs of one term, one document. But you see here that we don't have the term ID. We have a term, the full term, and the document ID. So now this is the logical representation of the same thing. That's the standard inverted index. If we rewind, in order to build this, to actually build this, we had to create these pairs somehow. And before they were grouped by term, they were just all over in the system, right? So maybe it was grouped differently. Like maybe if you rewind even more, then it used to be grouped by document, right? This is where the inversion happens, right? So first, it's grouped by documents in the original collection, and then you regroup by term and end up with the index. But again, we are going back in time now. We are rewinding the construction. So it used to be grouped by documents, and then you even had the original documents. But basically, if you rewind in that way, you notice that the pairs, they must be explicit, because since you need to group the postings by term and put the postings together that have the same term, then you need these pairs one way or the other, right? So the idea is that this is a waste of space, because you're just repeating CPU, 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 information, information, information. So this is not very convenient, and that's going to be filling the memory quite rapidly, right? If you actually really have these explicit term document pairs. You can actually do a few computations, and in fact, it's done in the book that we are using, where they took 1 gigabyte of text, 800,000 documents. So I really mean these are 800,000 documents or files, and the total size of these 800,000 documents is 1 gigabyte. This is what is meant here. And if you look inside, you will see that there is 100 million tokens. I really mean token, meaning the original tokens in the collection, right? Positional tokens. So there's 100 million tokens in my collection. And now you can do a few computations in this way. How much memory will it take if you parse these documents, you generate all of these pairs of term and document ID, and you compute the size that this means. So let's think a little bit. Let's assume that the terms on average have 10 characters, 10 bytes. It's an average, some sort of expected value. So in average, they have 10 bytes each. Then for the document ID, we can take 4 bytes. Why 4 bytes? Well, let's think. 4 bytes is 32 bits. So that is roughly 4 billion, right? 4 billion should be enough, because we said we only have 800,000 documents, right? So 32 bytes are fine in order to index that, right? Of course, once you index the internet, it's going to be more than 4 billion. So you need probably 64 bits instead of 32, right? But in that case, 32 bits is enough, 4 bytes. And then you just multiply 10 plus 4 gives you 14, 14 bytes times 100 million, that's the number of tokens, so the number of pairs. And that gives you 1.4 gigabytes, right? Just simple calculations give you 1.4 gigabytes for this collection. Note that this is more than the actual text. The text was 1 gigabyte, and when you parse it to the pairs, you actually need more space in memory than the original collection, right? This is not unusual that you have this sort of situation. Okay. Now, in another example, let's say we have 16 gigabytes of RAM. That's the working memory that we have. And now we are asking the question the other way around. So instead of giving you the size of the input and asking how much it is, I'm saying, okay, this is how much memory we have. What is the largest collection we can handle if we only have 16 gigabytes? So you just do the division, and you realize that you can handle up to 1,100 million tokens and up to 11 gigabytes of text, right? So you have 16 gigabytes of RAM. You can handle 11 gigabytes of text. This is ridiculously low, in fact. If you consider like an entire library or the internet and so on, this is like nothing. You won't go very far with that. And that's actually the motivation of this whole unit. How do we get better than that? And there are many, many ways today and next week that we will investigate to actually get better. So concretely, how do I solve that problem of redundancy? Well, there is something that is very popular in databases. It's called the dictionary encoding. That's the fancy name for what we are going to do here. But basically, we don't want to be redundantly writing the terms every time. We just want shortcuts. So instead of writing computer, I'm just going to write T3 or 3, right? Just T3 to disambiguate and make clear it's a term ID. But basically, I'm replacing all of these words with numbers, with IDs, right? And then, of course, I have to keep somewhere the mapping to keep track of what ID corresponds to what term, right? So I had the same thing with the documents. So I have a mapping from term to term IDs, but this is not really what takes space, right? So we assume we have that. And now we can recompute things. How well are we doing if we do it that way? Well, now, let's assume we have 4 bytes for the terms. Again, 4 bytes gives us 4 billion terms. That's a lot, right? The order of magnitude we had until now was more like 1 million, right? So this is 1,000 more. So this is very conservative. So 4 bytes and 4 bytes give us 8 bytes for every pair. Now it's a term ID, document ID pair. 8 bytes times 100 million tokens gives you 0.8 gigabytes. Now we are talking. Now we are smaller than the actual original collection. So how much do we fit now in our small laptop with 16 gigabytes of memory? Now we can fit 20 gigabytes of text, right? That's better than 11. So we are almost doubled what we can process with our working memory. And that's actually 2 billion tokens compared to 1 billion before, right? So this is a huge improvement, all right? For whom is that clear? All right. So again, a lot of what I told you is probably boring because you already studied hardware probably in more details than that, but I just wanted to make sure that you have the abstraction layer that we're going to use for the rest of the lecture. I have introduced the term ID, document ID mapping, and next week we are going to look into how we can more efficiently build the standard inverted index than we did in the Jupyter notebook in week 2. All right? So let me check how much you followed. It's normally going to be here. Of course. So this is the one. Okay, so just let me know. But hopefully it seems that you were following today. So wonderful. Okay. So that was a week relatively on the easy side. Very good. Okay, so thank you very much for coming and enjoy the exercise session tonight. Please note the email that 2 of the sessions are being merged into others, so make sure you come to the right one. I wish you then a nice weekend, and I'll see you next week for the continuation of the course. Thank you very much.